In the last video, we discussed the experimental work of Boyle, Gay-Lussac, Charles, Avogadro on gases in the 16th, 17th, 18th, and 19th century. We can combine all of that into a single ideal gas law. Along with that, we also want to give some terminology here. One of them is STP. It's often said that gas is measured at STP. This means standard temperature and pressure. For a given number of molecules of the gas, you need to know the temperature and pressure in order to define the state of a gas system. So really there are three things that you need to tell me. You need to tell me the temperature, the pressure, and the number of particles. Now, if you know three of those, then the fourth one, like volume, is known. We're going to find out that three of the four required, and a fourth condition called a equation of state is necessary to relate them. This is what the ideal gas law is. So STP is a temperature of 0 Celsius, but of course we don't want to work in Celsius, we want to work in temperature, so 273 Kelvin. And the pressure is 1 atmosphere, or 1.01 times 10 to the 5th pascals. An important result of Avogadro's number is that if you have 1 mole of a gas, then that mole of a gas, regardless of what type of gas it is, occupies the same volume. At STP, 1 mole of a gas occupies 22.4 liters. If you're at 2 moles, twice the number of particles, then it'll be 2 times 22.4 liters. This can be very useful on things like UIL tests and AP exams to very quickly be able to find the volume. Remember, volume is directly proportional to the number of particles according to Avogadro's. And if you're at standard temperature and pressure, 273 Kelvin in 1 atmosphere, you know the initial volume for 1 mole, 22.4. If you have 3 moles, it's 3 times this. 4 moles, 4 times this. Now, the ideal gas law combines all of these sort of facts. And what it says is this: the pressure times the volume, that was Boyle's law, is equal to the number of particles. We knew volume was proportional to the number of particles. That was Avogadro's. And we knew Charles' law said the volume was proportional to the temperature. So there's T. And there's some constant. And that constant is K. So this combines all of the various results that we had before into one nice equation. 4 things define the gas: the pressure, the volume, the number of particles, and the temperature. And this equation says that if you know 3 of them, the 4th one is known. We're going to show later that we can derive this by looking at Newton's laws and understanding of what's known as kinetic theory. This K has a very specific number, 1.38 10 to the minus 31 joules per Kelvin. And it's called the Boltzmann constant after Ludwig Boltzmann, who helped develop kinetic theory. Now, physicists like it in this form because we're going to see later on it directly connects to the physics going on, and we like to think of the individual particles moving around. But N will be a very large number. And so chemists and people who deal with it generally want to deal with moles, so that they don't have to deal with such a big number. Now, we can do that. What we do is rewrite the equation as this: PV equal N, the number of moles, times R times T, where N is equal to the number of particles divided by Avogadro's number, 6.02 times 10 to the 23rd, and R is K times Avogadro's number, and it's called the ideal gas constant. So all we did is took this equation and we multiplied by Avogadro's number and divided by Avogadro's number. This N, being in moles, is a much smaller number and it's liked better by chemists. You don't have a constant that has this very small value, because when you multiply by Avogadro's number, you raised it up quite a bit. It's 8.31 joules per mole Kelvin. By the way, you might have noticed that really Avogadro's is per particle, but we don't generally say that. So these are the ideal gas laws, and they contain everything that's known experimentally about an ideal gas. Now, what do we mean by an ideal gas? Generally, this is meant to be a gas of very low density, and it should be monatomic. But most real gases obey, at least at low densities, this law. We'll come back later and talk about why they deviate, and in fact, where this law comes from. This is the purpose of what's called kinetic theory. Now, I want to say one last thing I'd already started saying about equations of state. In thermodynamics, we have to define properties that define the state of a system. In classical mechanics, you say a ball is located at a particular position, x equal 3. And you might say it has a certain speed, at a certain direction, so it has a velocity of 10 meters per second. And you have a law, Newton's law, that tells you how to find the acceleration, which tells you how to find the change in velocity. With position, velocity, and Newton's laws, you can describe how the object will go through time. In this way, we got lots of particles moving around, and we don't see them microscopically. So how do you describe the system? In other words, how do you tell that one gas is like another gas? Well, there's 4 things. Temperature, they have the same temperature. They have the same volume. They have the same pressure. They have the same number of particles. Then they're going to be exactly and behave the same way. So there are just a few parameters in a thermodynamic system that defines it. And for a gas, this number is these 4: temperature, volume, pressure, and particles. The interactions between the atoms, the forces that exist in Newton's laws and such, that are one, mean that these 4 things cannot be completely independent. In fact, they're connected. They're connected by what's called an equation of state. Now, the equation of state may be difficult to find or may only be able to be found experimentally, but there is an equation of state somewhere that describes the relation of one of these parameters to the others in terms of fundamental physics. The most famous equation of states is the ideal gas law, which says if you know 3 of them, say V, T, and N, then you also know P. Or if you know P, V, and T, you also know N. So give me 3 of them, and I know the 4th. A lot of times, people are working problems with a fixed N. Since N doesn't vary in the problem, for a given T, we just have to know P and V. Because if we know P and V at a particular instance, for a fixed N, we know T through the ideal gas law. And as the system moves, say from this point A to some other point, say B, maybe it moves like this and then down here, then at each point along the path, we can tell you its pressure, its volume. Then by the ideal gas law, given that we knew the N from the initial, we can tell you T. So I only need to plot P and V and have the ideal gas law to tell you everything about the system. These diagrams with pressure and volume written are called PV diagrams, and they're going to play an important part in later chapters of this course. All right, that gives you some idea about equation of states and about ideal gas laws that you can use to actually solve problems. Next, we want to go into the fundamental physics about why the ideal gas law looks the way it does. In short, we want to derive the ideal gas law, and most importantly, I want to get back to our original question. What is it that temperature is really measuring inside the gas? What is it telling us? In fact, what is this P and V over here telling us? What is this N telling us? We're interested in these sort of questions. Fundamentally, what are these things telling us at the microscopic level? And we're going to do what's called kinetic theory. And from that, we're going to get a relation between temperature and the internal energy of the molecule of gas. So in other words, the energy per molecule, I'm going to claim, of a gas is related to temperature, and I'm going to get that specific relationship next time. So that's what we'll do next time.